3D printed rod networks, multi-material thin shells, and multi-layer laminates are examples of structured sheet materials whose microscale composition gives rise to complex macromechanical behavior. Simulating structured materials on their native scale is often computationally prohibitive for real-world problem sizes. Numerical homogenization is a common strategy to reduce complexity while accurately capturing the macromechanical behavior. With a sufficient number of uniaxial and biaxial stretching tests, the often nonlinear in-plane behavior of the material can be determined. In principle, an analogous strategy can be followed to characterize the out-of-plane behavior using uniaxial and biaxial bending tests. However, double curvature states cannot be obtained without violating periodicity conditions, and the response to double curvature cannot be derived directly. When subject to bending along a given direction, finite-sized samples of material will generally tend towards a double curvature state. Our key observation is that this preference also manifests for cylindrical bending in the form of non-zero bending moments in the direction orthogonal to the imposed axis of curvature. Therefore, uniaxial bending tests would be sufficient for inferring curvature coupling, if the bending moments are also taken into account. Since bending moments are typically not available in the native scale simulation, we follow classical plate theory and compute bending moments by integrating stress tensors through the thickness. By performing uniaxial bending tests with different magnitudes and directions, we obtain energy moment curvature data, which we use to fit a nonlinear bending model represented by a neural network. The neural network trained on these data shows that our approach for computing bending moments is consistent with the curvature energy pairs in the simulation results. To further validate our method, we apply a fixed level of longitudinal compression to a finite-sized patch, and compute the principal curvatures at the midpoint of its midsurface. We then compare quantitative results between native scale models and our homogenized models. We apply our moment-based homogenization approach to a large range of sheet materials and native scale simulation models, including discrete shells with heterogeneous material properties, multi-layer sheets modeled with solid shell elements, thin networks made from discrete elastic rods, scaled sheet materials that exhibit contact-induced stiffening during bending, and thick structured sheets modeled with quadratic tetrahedra as shown in the previous slide. Materials' double curvature response also strongly depends on their widths. To study this width-dependent behavior, we create thick structured sheets with smaller and larger widths, perform compression experiments on them and plot their Gaussian curvature. The Gaussian curvature produced by the native scale model decreases with increasing patch width, which aligns well with our homogenized simulation results. Our quantitative analysis also shows that our new moment-based homogenization approach outperforms existing baselines in terms of accuracy with respect to native scale simulation data.